Hello, and welcome to Lesson 9 of this Introduction to Probability of Wolfram U. The topic for this lesson is continuous random variables. Let's begin. Imagine the same waiter as the last lesson, still responsible for distributing water to clients. Clients ask for any amount of water, from a drop to a full glass, randomly. Then the amount of water asked is a continuous random variable, meaning the probability of asking X amount of water depends on the real number X. Notice that we'll use integration in this lesson, but don't let that scare you if you're not familiar with it. This course uses integration purely instrumentally. In this lesson, you'll learn about continuous PDF, CDF, expectation, and plotting. This is intentionally similar to the last lesson to show you the similarities and differences between discrete and continuous random variables. Consider this: the most common type of random variable is continuous. We use the term probability density function for all random variables, but the term was originally coined for continuous random variables. You can already guess the analogy. A metal rod with different densities along its length is similar to a probability density function with varying probability. For example, consider a polarizing pole with PDF 3x power 2 divided by 2 for x from -1 to 1. 1 means completely agree, and -1 means completely disagree. Go ahead and write the function, then make it a probability distribution. Notice the range doesn't have an increment because it's continuous. As another example, consider rain landing uniformly in a triangular field of length 20 and width 10. If x represents the x-coordinate, x divided by 200 would be the probability of width on the length. To confirm the validity of this PDF, you can see here the function is always positive, and integrating the function over the domain x, you can see the total is 1. Now that you've confirmed this is a valid PDF, just write the function out, then the distribution. The continuous cumulative distribution function is still the probability that x is less than or equal to I inclusively. This is the integration of all PDF probabilities from the beginning to I. This is the symbol for integration. All you have to change from the discrete CDF is replacing the word sum by integration. Let's say in the poll example, you want the probability that the value is less than minus 0.5. So just write the CDF with integrate and compute at minus 0.5. For the rain example, what's the probability a random raindrop falls between 5 and 10 over the length of the field? You can try to compute this geometrically, since the shape is quite simple, but we'll use probability methods. So let's see. First, we could use a two-ended CDF with parameters for the start and end of the interval. Evaluated at 5 to 10, you get 3 over 16. Second, use the CDF of the distribution. Since taking the CDF can by default only go from the beginning to I, you can artificially get the probability from A to B by taking the CDF of B minus the CDF of A, as shown here. Most intuitively, you can use the probability function between 5 and 10 to get this result. It's worth noting that discrete probability differs on the inclusion of discrete values, but continuous probability doesn't. In the discrete case, each value has a probability associated to it, whereas in the continuous case, a single value has a width 0, so an area 0, which would mean that it does not contribute to the probability. So here, adding or removing equals is trivial, as you can see. Of course, continuous random variables also have an expectation, calculated using integrate instead of sum. As you probably guessed, the metal rod analogy extends here too, as the center of gravity is equivalent to the mean. Consider taking the mean of the poll example considering only approvals, that is, only positive values. You could consider this a conditional probability and divide the integration of the mean from 0 to 1 by the integration of the probability from 0 to 1. Much more intuitively, you could take the expectation of x with the conditional that the approval is positive over the distribution. What about the expectation of the square root of x for the brain example? Similarly, you could integrate the square root times the probability of rain over the entire domain, or just take the expectation of the square root over the distribution. Let's go back to visualization. Continuous distributions are more popular, so there's many ways to visualize them. In this course, we'll focus on four main functions: plot for one variable as a function, histogram for one variable as data, plot 3D for two variables as a function, and histogram 3D for two variables as data points. Notice during the entire lesson, I never visualized the polarizing pole example. Why do I even call it polarizing? Well, check for yourself. How would you go about visualizing the pole example? One option is to visualize the function of the random variable directly. So just plot the pole function on the domain. Since continuous probability usually expresses the area under the curve above zero, I like to add the option filling to bottom to best visualize. Clearly, you can see most people either strongly agree or strongly disagree with this distribution. This visualization could also be done by plotting the PDF of the distribution to get the same results, or you may want to see the CDF of the distribution, which also shows a high increase close to -1 and 1. Okay, let's do a real example, taken from an old exam P, the professional actuarial exam for probability. An insurance company insures many homes. The insured value of a home is a random variable following the PDF 3x power minus 4 when x is greater than 1. Assuming the value is at least 1.5, what's the probability a home is insured for less than 2? With the Wolfram language, we can actually solve this in a single line. First, your probability distribution is 3x power minus 4 from 1 to infinity. Then we can take the probability of x less than 2, considering that it's greater than 1.5. And you have your answer. The probability is around 58%. So to summarize, continuous random variables have continuous PDF values. For PDF, CDF, expectation, and more formulas, the main difference between discrete and continuous random variables is the change from sum to integrate. Use plot, plot 3D, histogram, and histogram 3D to visualize. But we've barely scratched the concept of expectation. There's a lot more to characterize random variables than just average and plotting. In the next lesson, we'll dive deeper into different characteristics of random variables based on the concept of expectation.